With the introduction of large language models, software engineering has been perpetually 6 months away from extinction for the past 3 years. Obviously, vibe coding still has a ways to go, but peering ahead, how can we stay relevant? The answer is visual scripting, or visual nodegraphs, if you will. I asked ChatGPT to write me a visual scripting language and an editor to go alongside it, but it looks like it's not quite... Jesus Christ. Maybe it is there. Damn, let's see if this works. Like I said, it seems like it's not quite there yet. I wasn't even worried. So, for now, we'll have to write our own. But how? Well, let's figure that out together. So grab your coffee, tell your lead this is research, and let's get started. Now before we can get to pumping out some really sick code in hopes of setting up the foundation for our visual scripting language, I think it'd be wise to have a look at some of the existing languages out there and perhaps take some inspiration from how they're doing things, as well as figure out what we don't necessarily love about their approaches and how we could do it differently. Actually, that sounds kind of boring. So why don't we just wing it? In fact, in doing so, we're not influenced by their approaches, and we're even more likely to come up with something truly unique and groundbreaking. So with that settled, now we just have to figure out how to make a node graph. So to start, we won't worry with making it optimized. Since we don't know the requirements yet, we also don't know how to make it performant, so there'll be a lot of wasted effort. Instead, we'll just do it as quickly and dirty as possible with this first iteration. In order to take our node graphs to the next level, we'll of course need the basics like nodes and graphs. But there's also one more thing that we're currently missing: a UX designer. And unfortunately, I can't afford one. So I'm gonna be taking on this role myself. But don't worry, I'm actually surprisingly slow when it comes to understanding tools and UX, which is perfect, because if we can make something that's easy even for me to use and understand, then we'll know that we've effectively lowered the bar of entry to a record low level. So with that out of the way, to start us off, we'll first create some base classes for the nodes and node graphs, with the nodes holding their respective positions and the graphs holding a map of nodes. Now I know what you're thinking, why waste precious memory on the position when it's purely visual? And you're right. But did you ever stop to think that making this world a little bit more beautiful maybe is the most important task we have? Leave it a little better than you found it. But no, don't fret, it's only temporary. Like I mentioned before, we're just trying to get it working first. We don't care about performance yet. So what's next? Well, currently we just have nodes, but we have no way of connecting them, and thus no way of passing data in between them. And without that, it's pretty useless. So we'll add a pin class that can take a template to make it easier and quicker to add type pins to our nodes. Since nodes can have inputs and outputs, we'll need in pins and out pins, so we'll add an execution type to differentiate them. I think it'd be useful if the pin also holds a reference to its owner, as well as a list of what other pins it's connected to. Sprinkle in a few utility functions like connecting and disconnecting pins, and with that, we now have the basics for setting up our node graph. We'll just add some visual representation for the nodes, pins, and the links in between them, and with that we can now start creating some of our very own special node graphs. Now wouldn't it be nice if we had some actual logic to execute when traversing the graphs? And to do that, we need to know where we want to start traversing the graph, in other words, where our entry or result node is, depending on the type of graph we're traversing. And in a possibly futile attempt to try and stay a bit more consistent with our terminology here, I think it's worthwhile deciding on what kind of graph we'll make as our first one. Since my career thus far has been one as an animation programmer, an animation graph seems appropriate. Animation also just happens to have the funniest and most bonkers bugs. With that in mind, we'll be using a result node as our entry point, and our graph will therefore hold a result node ID. Since we now have the makings of a result graph, it feels fitting that the function we'd use to traverse the nodes of the graph would be called evaluate. Make it virtual so we can override it with custom logic depending on what type of node it is, and have it take an evaluation context, which can hold any data necessary to evaluate the graph. For now, we'll leave it empty, but this way we don't have to change any derived functions in the future when we eventually want to pass on more data down the graph. Now that we have a way of traversing and evaluating the graph, we just need to add a few different types of nodes so that the graph can actually do something. Since it currently can't play any actual animations, it's a bit of a stretch to call it an animation graph. So I think the biggest bang for our buck at this point would be to create an animation clip node. If only, Clippy, if only. For that we need an animation clip, a looping flag, a current time, as well as a pose pin as its output. A pose in this case holds a collection of transforms, which in turn consist of a position, scale, and rotation, and together these transforms describe the state of an animated skeleton. We won't store any of this data in the pin itself, however, but the pin will act more as a binding to the evaluate call of this node. The evaluated pose is passed through the evaluation context in the node's evaluate function, meaning that we don't have to worry about copying around large swaths of data, so it'll actually be just a teensy bit more performant, even though technically we aren't supposed to care about that right now. Let's also add a node for blending between two poses, taking a ratio between 0 and 1 as an in-pin. Perfect! Now that we have that compiling, let's try and run it and see what happens. That doesn't look quite right. But on the other hand, this is one of the reasons why I love animation programming. You get the best bugs. But what's going on here though? Right, I forgot this animation was exported with an updated version of the mesh. So let me just re-import the mesh real quick and let's try it one more time. It's alive! Damn it. That's so dumb. Now that's cool and all, but Papa Gabe ain't gonna be impressed with a static animation graph. We've basically created a fancy and incredibly unperformant way of combining animations that's highly inflexible. We've essentially created a metaphorical fridge. If only there was a way to make it a bit more flexible. Can you see a way to make it more flexible?
Do you see the wall?
Can you see it anywhere? That's right, graph variables. Woo! With graph variables, we'd be able to make the graph dynamic, and with our current modest amount of nodes, we could do a lot. So let's add variables to our graphs. The variables will hold an identifier, in other words, the variable name, and a value. Since it can be any type of value, let's call the type blackboard value. Blackboards are usually referred to as a way of storing a bunch of different mutable values, since, like a blackboard, you can write any value you want to it, and similarly, you can also read any value it holds. For now, we'll just create some of the primitives we'd want, like a bool, int, float, float2, float3, float4. We'll of course need a way to access the variables in the graph, so a getVariable node seems appropriate. Without a way to set the variables from outside the graph, we haven't really solved the problem. We just pushed it further up. After adding that to the API of the graph, we should now be able to dynamically blend between animations. I know this might look like it's bugged, but this is actually the expected result. It may not look like much, but trust me, we can already do some really interesting things with these limited tools. Now in the past, I've worked with some truly monstrous engines that basically only had this logic exposed to designers and animators. Now mind you, they did have a lot more animation tech going on top of that, but it wasn't very easily available to the animators. They always needed a coder to be able to make meaningful changes to the logic, and that is one of the main reasons for why I'm so drawn to Visual Nodegraphs. The power they're able to give content creators is borderline immeasurable, and as a programmer, it makes me even more excited to create even better tools and features. And to do just that, by adding a state machine node and an associated state graph type, it would allow us to more cleanly separate our logic as well as establishing entry and exit conditions for different states. A good example of a state machine use case for animations would be locomotion. It's likely that you'd want different logic and behavior for running, jumping, flying, and swimming, and you'd sometimes want specific transition animations to play when going in between them. And that's where a state machine can prove to be incredibly useful. So for this new state graph, we'll have nodes like before, but in this graph we'll only have access to two types of nodes, state nodes and transition nodes. Each state node will hold an animation blend graph in it, which is the graph we worked on up until this point, while the transition node holds a result graph, with the result being true or false depending on if we should transition or not. Because a state needs a condition to transition to another state, otherwise it would never actually play itself, we'll have to connect states together with transition nodes. Meaning that the state node will have both a transition in and out pin, accepting multiple connections. The transition node, however, only accepts a single connection for both its state in and out pin. And with a few more clickety-clack-clacks and compilation clunks, this is what our locomotion state machine looks like. Not gonna lie, it's not the prettiest, but I think I have an idea for how to make this a little cleaner. We'll hide the pins, make the state nodes look like little spaceships with shields, and then we'll make the transition nodes into arrows pointing in the direction of the state it's transitioning to. Then, as an extra flex, if two state nodes have bidirectional transitions, we'll join the arrows together to a doubly arrow. Whew, yeah, that's the stuff. Here's an example of the type of results we can achieve with these node graphs, with some animations very generously supplied by my good friend and animator Tobias Künster, along with a model created by my very talented friend Jamie Baudo. Meanwhile, in performance land, all hell is breaking loose. Cache misses are running rampant, and CPU cycles are dropping left and right like flies. We've sacrificed our brethren for another type of speed, and I think it's time for us to show our own people some respect. Show them that there's a world where not every other instruction goes to waste. One where we can stand hand in hand, in sequence, and keep the caches of Nevor intact. But how? Well, let's try and tackle some of the worst offenders one at a time. Depending on the size of our skeletons, evaluating the poses can require a significant amount of memory. Not in terms of our whole RAM, but in terms of our much smaller caches. Since a skeleton with 100 bones, which is not crazy by any stretch of the imagination, would have 3 float 4s, one for position, rotation, and scale respectively. So that's 48 bytes times 100, which equals to around 5 kilobytes. And that's just one pose. While we are traversing the graphs, we'll already have the nodes and their data in memory, but once we read from an animation clip or blend multiple poses together, a significant portion of our caches will quickly become invalidated. So what's something we can do to try and avoid this? Quick side note, if you're unfamiliar with what a memory cache is and why you should care, I highly recommend checking out my other video on particle systems where I go through the importance of how your memory is laid out in regards to best utilizing the CPU's caches. But to try and mitigate the cache issue, in this case, we can split up the traversal of the graph nodes and the actual skeleton pose evaluation into 2 separate steps. That way we don't access any bone information until we've fully traversed the graph. But in the second step, how do we know which animation clips to use, at what time, and how we should blend them together? One way of doing it is to fill out an instruction stack as we're traversing the graph. Let's go through some of the examples of what this could look like. In the example of just playing a single animation, it's pretty straightforward. We have a push pose instruction, which is always present since we always want a result pose, and an animation clip instruction that holds the particular clip index and the evaluated time of that animation clip node. Now, in the case of blending 2 animations together, things get a little bit more interesting. Just like before, we have an initial push pose instruction. Then, as we get to the blend node, we first traverse down blend input A, which in turn adds an animation clip instruction. We push another pose, otherwise the second animation clip instruction would just overwrite the first pose. Traverse down blend input B, where we add another animation clip instruction, and then finally we add our blend instruction at the end. Now that we have our set of instructions, let's see how they actually play out. In our first example, we have the following. We push a pose, which starts out empty. The animation clip instruction fills out the pose from the animation clip at the specified time, and that's our resulting pose. Now for the case with a blend, similarly, we push a pose and fill it out with the first animation clip instruction. Then, we push another pose and fill that one out with the second clip instruction. And now the blend instruction takes the top 2 poses and blends them into a single pose, which in this case is our result pose. What you might be able to tell though from this way of setting up the instruction and evaluation is that we already have support for nested blends. If we add another blend node into the mix, this is what it'd do to the instruction set, and the evaluation of the pose would simply have another step to it. With that taken care of, we've now significantly increased the performance of our animation graphs. And a neat little side effect from this change as well is that we can now lazily evaluate the animated pose for only the entities that are on screen, or whichever ones we care about, while still traversing the graphs for logic changes off screen. This is a huge win and is extremely useful, especially when dealing with servers that want to validate actions without having to run expensive animations for everything at all times. Now another big optimization is one that I'll briefly cover here, as there's just too much to fit into this one. And that is the separation of asset data, in other words editor-side data, and resource and runtime data. Because the requirements for editor and runtime data are so vastly different, with editor-facing data needing a lot more information like editor attributes, display names, and functionality to listen to changes, while runtime data needs to be as tightly packed, small, and efficient as possible, it made sense to me to have more than one version of these data types. The main problem with this approach, however, is that it's incredibly boilerplate heavy. In other words, you'd have to write mostly the same class or type at least twice with very minute differences, and anytime you change one, you'd have to remember to change the others. To call it error-prone is a gross understatement. So I came up with a solution, which is taking inspiration from Unreal's approach to generate code based off of tags, but instead of having the tags live in C++, I created my own C++-like markup language called Cog, which is short for code generation. In this language, it creates multiple versions of the same data based off of tags, examples being editor-side, binary stored on disk, runtime versions, as well as an automatic step that is able to compile the editor version into the resource version. Having worked with many engines in the past where a lot of this type of work had to be done manually, I wanted to create something where most of this was handled automatically. And on top of that, I wanted whatever code was generated from it to look like code that a human, this human, wrote. So, without realizing it, I started writing a parser, a compiler, and several code generators, which was a ridiculous undertaking, now looking back, and not one I ever thought I'd commit to. However, the amount of boilerplate code that it saved me from writing, and in turn the endless amounts of small errors I no longer can make, has been such an incredible time saver. In my codebase of around 150,000 lines of code, around 30,000 are generated through my cog files. Now getting back to the task at hand, I've gone through the work of refactoring the graphs and nodes into the cog file format, and this is what it looks like in the case of the animation clip node. And this is code that it generates for the asset data and resource versions respectively, as well as the code that converts or compiles from asset data to resource. You can probably see the benefit of having this code be auto-generated, as it's mostly just a lot of tedious boilerplate. Now that all the data related to the nodes is tightly packed, traversing the graphs is now even faster, further reducing the time of that first optimization we did. And with that, I think we'll call it a day. I have many topics I want to cover in the future, like how to extend this node graph system into a scalable visual scripting language, and all the things that come with that. Instancing, a more comprehensive pin type system, callbacks, and so much more. If there are any topics you want covered, or if you have any opinions of what we covered here today, I would love to hear your thoughts and suggestions down in the comments. A huge thank you and shout out to my patrons, as you are truly what keeps this thing going, with an extra special shout out to Slim B and Icarus. If you want to help support further development of the engine, you can do so by becoming a member over on my Patreon by following the links in the description, where you can also find a link to the engine executable, as well as our community on Discord, where we talk about all things code, game, and engine development. Thank you so much for watching until the very end. I hope you have a fantastic day, and until next time, take it easy.